Okay, so I think we can start. So first of all, thank you very much for being here, either in person or connected through Zoom. So this is the 5th seminar organized by the Italian Institute of Artificial Intelligence, jointly with the Institute for Advanced Studies here in Turin. And the scope of these seminars is to touch fundamental problems in current AI by inviting experts in the field. And so today I'm really very happy to have participated a bit in the organization of this seminar in inviting Pietro Perona from Caltech. Pietro is really a reference person in artificial intelligence. He has done fundamental works in vision and fundamental work at the root of AI. For instance, he has created very important for instance, data set that have allowed algorithm to make enormous progress toward what we see today. So Pietro is the kind of scientist who can really merge theoretical and conceptual aspect with concrete and as important practical algorithm and data structures. So today Pietro is going to talk about causality, which is a fundamental problem in AI and in general. It's a fundamental problem. So please, Pietro, I leave you the floor because your seminar will be more interesting than whatever I can say.
So good evening, everyone, and thank you for inviting me. Thank you, Fabio, for inviting me to speak to you today. And today I'm talking to you about responsible AI, and I have to start from AI. What is AI? And in the last 20 years, 3 things happened that made it possible. And so one is ideas from neuroscience from the 60s on how the brain is wired and how the brain processes information in cortex, mostly visual cortex, that inspired thoughts about deep networks. And so that's certainly something that was there in the 90s when I got my PhD. The second thing, you saw it in the previous seminar from Bill Daly, GPUs, Moore's Law, lots of compute, that's fundamental. And the last ingredient that fell into place is what Riccardo was talking about, namely large annotated data sets that allowed us to understand that deep networks are not just a toy, they were for real, and they could solve difficult problems. And as you know, this last branch has kept growing in the last 15 years, and now we have models trained on billions and billions of data, images, and text, and this is what gives rise to what we call today AI. Now, whether it's really intelligent or not, we can probably talk about it in the panel discussion afterwards. Now, in the last 5 years, so I have worked for my whole career in this field, starting from computer vision, and it was always a very interesting academic pursuit. We were excited, but certainly were not very interesting for the rest of the world. And in the past 5 years, we've become interesting for the rest of the world. And it was with great joy that I saw that people could use what I was working on. And at the same time, some dismay because society reacted in a fairly violent way sometimes and pointed fingers at us saying, oh, you're not doing a good job one way or another. And so I became involved in the question of responsible AI. I wanted to know what does society want and what can we do to make things well or better for society. And so that's the topic of today's talk, is my own travels in this area. So there are many things that we would like to do with AI. So I list them here. You can read them quicker than I can say them. And there are societal concerns that we have to take very seriously. And today, I'll mostly focus on the question of fairness and bias. So the other ones are equally interesting and important, but I want to go deep into one thing, and so I picked this one, fairness and bias, and a little bit explainability, but not so much. And by the way, I will be very interested in hearing your questions at the end, so hopefully there will be enough time for people to ask questions. Your concerns are interesting to me, so I want to hear about them. Okay, so bias and fairness, and this is an article that came out on the website ProPublica a few years ago, and it concerns software that counties in the US use to evaluate whether a prisoner should be given parole, whether the prisoner should be released ahead of the end of their sentence. And the key question is, does this prisoner constitute a danger for society, or are they harmless, and so they can go out and reintegrate in society earlier? And the reason why people use software is because the parole boards, namely the lawyers and judges who give parole, are very different in their approach from county to county, and therefore okay, I have it here. Thank you. And therefore, it was thought that maybe AI can help analyzing the curriculum vitae of the prisoners and give the judges a uniform evaluation. And evaluation is a score, and the score from 0 to 10 is the level of risk that a person presents to society, and hopefully that will uniform the application of the law across the different counties. But as you can see here, at some point there was a huge concern that maybe the software is biased against black people. And that's, of course, a disaster. So is that a problem? And so I will go in detail into this case and explain to you how to analyze it. Not only that, but you know, all of you have come into the European Union or the United States, have used cameras to be recognized, and now face recognition technology is ubiquitous, and so there is a concern of whether it works well or not. So we have a new problem with the monitor. And so people are arrested by the police based on facial recognition. So is it biased? Is it fair? All of that. And this is reflected in articles in the newspapers. So how do we know if these concerns are correct? And how do we figure out what to do about them? Namely, we're engineers, something doesn't work well, we want to fix it. What do we do? And so that's the question. Now, it's important to remember that bias was not invented by AI. Bias is in society all over the place, and sometimes biases are reasonable and sometimes they're not. So here, without expressing a judgment, this is the population of prisoners in the US. And as you can see, the frequency of being put in prison is different for different ethnic backgrounds. Okay, so that's a bias. Is it justified or not? And the biggest bias of all is between men and women. So there is a factor of 15, about 15, between 15 more men than women in prison. Huge bias. Is that something that we should worry about? And here is a score on the SAT, which is an exam that is taken by kids going to college in the US. And it's very biased vis-a-vis the income of the parents. That's a fact. Is that a problem or not? What do we do about it? Here is another case, even more subtle, which was reported by the Los Angeles Times. 2 identical twins apply for asylum in the US. It turns out that their application is processed by different bureaucrats, and they get completely different outcomes. You know, how come? What is happening? So it's clear that not only people working on AI have the duty to do a good job and to know that their systems are unbiased, but there is a tremendous opportunity to help in society avoid situations like these ones. And probably if we can automate processing of information, such as an application for asylum, we can avoid this kind of situations. At least we can flag them. So today I would like to tell you about 3 things. So it's very simple. One is definitions. How do we talk about these quantities and mathematize them so that we can analyze what's going on? We can look at data and discover if there's a problem. The second one is enabled by the definitions. How do we express goals that society wants to achieve? And I will show you that it's very difficult. So we have to be very clear about the goals, and we can achieve one goal at a time, but not all the goals at the same time. And the last one is, how do we know what's going on? How do we measure the behavior of AI systems? So people use different words to refer to fairness. And so there are these two words used in the US, equality and equity. How many people know the difference between these two? Okay, so the drawing makes it clear what this means. And so equality means that everybody is treated the same, everybody is given the same opportunity, if you will. And equity means that the outcomes are the same. That's how this term is used in the US. Now, which one is right? Well, at least we can try to capture in mathematics, and this will be the only equation I have here for the people who want to see a little bit of math. And so the idea is that the AI system or a process that includes AI systems is a function that maps some information about a person, like the actions of this person or the state of this person, and some information about their protected attributes, which would be sex, age, race, that you want to be unbiased towards, and then this function creates some outcome that you have to evaluate. And so you can write equal opportunity by saying that the protected attribute shouldn't make a difference. Or you can think about equal outcomes, saying that whichever way you are on that, your outcomes should be the same in probabilistic terms. Okay, so these are just two examples, and there are many, 20, 30 different things that you want to look at. For example, what's the probability of positive outcomes or the probability of negative outcomes, the false alarm rates, and so on. There are different things that may matter in different situations, and the important thing is that you write them down mathematically to be able to analyze them. And so let me go through some examples to show you that society comes down on different sides of these choices in different situations. And here is the winners of the 2019 New York Times Marathon, the New York City Marathon. And if you look at who wins the marathon, it's always East Africans. Okay, one exception, there is a person from the US, but in fact, she's, I think, from Ethiopia, and she was naturalized in the US. So it's clear that we have equal opportunity in as far as ethnicity. So if you're Japanese or Italian and you say, how come no Italian is ever winning? And people tell you, well, you can buy a pair of shoes, just run faster, and then you get your gold medal. Okay, so clearly, for the marathon, if you look at men or women, we have an equal opportunity sense of fairness. If you can run and nobody blocks you, that's fair, and then you can compete. But it's also true that the number of winners for men and women is the same. But you see that the time it takes for the women and the men is different. So when sex is involved, we are in an equal outcomes choice, and everybody thinks that it's fair that the women get to have a winner as much as the men get to have a winner. So in the same race, we have equal opportunity when ethnic background is concerned, and we have equal outcomes when sex is concerned. Is this good or not? Well, we chose it, right? So society, or this particular sport, decided that this is the right way to go. Now, I want to emphasize that other sports make different choices. For example, in horse jumping, men compete with women, and there is only one medal. It's not separated. And so here you see the Olympics, and only 2 women has won some medals in the 10 years from 1990 to 2016 or whatever. Okay? So equal opportunity. Now there is another specialty in horse racing, which is dressage. Some of you know about it. And here the men are very few, and women win most of the medals, and nobody is worried. So as you can see, in different sports, you have different practices. And if you look at wrestling, it's divided up, and boxing, they're divided up by weight, which is more or less a proxy for ethnicity. So there are the Turks win all the lightweight, and the Samoans win the heavyweight, and so on. So every sport has their own way of being. And so what I would like to emphasize is that the choice of what's fair is established by tradition and by society. And the important thing is to be aware of it and being able to write down an equation that describes what society wants. And then people in AI can try to achieve that, that criterion. Now, I would like to come back to this case and explain to you what happened. As I told you, each candidate for parole is assigned by the algorithm, assigned a score for how dangerous they are. And if the score is 5 or better, 5 or higher, they are deemed to be high risk. And if the score is lower, they are deemed to be low risk. So what was it that worried ProPublica? It was that they looked at the statistics of what happens, or what was the score for people who were released and were checked after 2 years. Did they reoffend? Did they commit another crime or not? And so amongst the ones who had not committed a crime, you see that the high-risk ones were 23% white and 45% black. So this means that people whom we suppose, since we didn't do anything bad for 2 years, people are fine, half of them, almost, of the blacks, were given a bad score. So had the algorithm been used, in their case, they wouldn't have been let out. And that was much less prevalent for white people. So that doesn't look good. And vice versa, for people labeled as low risk. Okay, so looks like there is a huge bias. And this is completely wrong. Now, Alexandra Chudachova, a couple of years later, looked at the data, and she pointed out that if you do a different analysis, namely, you look at the score, which is at the x-axis here of the plot, and you look at the probability that the person with that score gets, after 2 years, to be a criminal again, there is no difference between whites and blacks. Okay. Now, how is it possible that both things are true, that the algorithm is highly biased and you should never use it, or the algorithm is perfectly fair and, in fact, it picks up quite a bit of the risk that there is for reoffense? In fact, if you look at the score, it's highly predictive of how things are going to go on, and it has no bias between blacks and whites. How could you have both things at the same time? And so this is one of those questions that people had to tackle and realize that there is a fundamental difference in these two ways of analyzing the data, and society has to come up with a decision as to which one they want to use. So what's happening here is that the two populations of blacks and whites, which are the two that were looked at, are distributed differently vis-a-vis the scores. And so you see that for the blacks, the score, the frequency of the score is almost constant, it's a uniform. And for the whites, it's highly peaked for low scores. So it turns out that what you're doing here, in the high part of the plot, where it looks bad, you're conditioning on whether people are reoffending or not, and you're looking at statistics by conditioning on that. And in the other plot that Alexandra put out, you're conditioning on the score and checking what it predicts. So you're doing the opposite. And let me convince you that the two things can go that way. So in this example, I use men and men are darker and women are lighter as dots. And so let's suppose that we have a sample of 18 people, half men and half women, and we score them. And so 1 means high risk, and 0 means low risk. So you see that here there is a bias, and the men got more frequently a high-risk score than the women. But we could say, well, we know that men are more violent. Maybe it's reasonable, right? Who knows? Now we wait for 2 years, and we see which one of them did reoffend and commit another crime. And we get to observe them. And you see that in the low-score region, fewer people committed a crime. In the high-score region, more people committed a crime. That's reasonable. And we also see that it's unbiased because the same fraction of men got the same type of error, either a false positive or a false negative. Okay, you see it because they form columns. And so this looks perfectly unbiased, and it's fine. However, if now we group these people by whether they did reoffend or not, and we count how many there are, you see a huge bias. And so you see that on the left side, amongst the people who did not reoffend, half of the men had gotten a high score, but only 1/5 of the women had gotten a high score, and vice versa on the ones who committed a crime. So if you predict based on the score, it's unbiased. And if you postdict by looking at what happened afterwards, there is a huge bias. Okay. So this is one of those cases that unless somebody spends the time to figure it out, society doesn't know, and you think that there is a huge bias, and you have to be very careful. So I just wanted to make sure that people get to see these examples because they're quite instructive. And so California decided that the important thing is prediction, because you come in front of a judge before the future is adjudicated, and you want to know if this person is likely to commit a crime or not. That's the only question that matters at the time, and postdiction is not. And so the law now says that you should look at the scores before the facts and predict. Okay. So this is an example of how intricate this work that society makes in deciding which ones are the important characteristics. And so here, the example comes from the New York Times, again, from the Globe Theatre in London, who put up Richard III last year. And the director is also an actress, and she decided that she would be Richard III. Okay? Now, you could say, fantastic, I want to see a woman do Richard III. It's very interesting. No problem at all. In fact, fantastic. But there were complaints. So what were the complaints? Well, the organization called the Alliance, the Disabled Artists Alliance, said that since Richard III was a disabled person, only a disabled actor should be playing the role of Richard III. So they said, there is a huge bias. You're putting an able-bodied actor in a role that belongs to disabled people. And the production said, no, that's not the case, because Shakespeare never meant for actors to be the literal impersonation of the characters. And there is freedom, artistic freedom, and the actors should be able to do whatever they want. So you see that these debates come up all the time. And society has to resolve them themselves. You cannot look at AI and say, oh, AI should solve it. No, society has to decide. And so that's a human province. It's not an automation province. Okay, so what we've learned is what are the criteria for fairness, the fact that some attributes sometimes are protected because society decides that those are important and you cannot discriminate based on those. And you cannot be fair according to more than one of these criteria. Either you satisfy one or the other. They are intrinsically different. And unless you're lucky, you can only satisfy one at a time. So society has to have a conversation and decide what's important. And then engineers can come along and implement what society wants. Okay. So now we get to the third part, which is measuring bias. And that's very tricky. And so I want to show you how sometimes you can tackle it in a way that is convincing, at least to me. So I want to talk about face recognition. And so when you enter the US, you either have an employee looking at your photograph or there is a machine. And it turns out that by now, machines are much better than humans at recognizing human faces. And I'm making a statistical statement here. And the fact that humans are bad at recognizing faces is extremely well documented. So there are ample studies showing, especially these studies are done for witnesses in court, and it's abysmal. And so the national academies have a report out telling the courts don't trust eyewitnesses unless there is other evidence. You cannot trust just a person who says, oh, you recognize that person. Okay, so here is another place where machines, if they're available, and now there are cameras everywhere, in principle, machines should be better at solving crimes when you can recognize faces. And so it's really important to know that machines are unbiased and they can work well. Now, this is to show you that people also know why humans sometimes are wrong in recognition, or one of the reasons. And so there's a study out of Stanford showing that, for example, here, subjects in a psychophysical study coming from European background are bad at recognizing faces of African Americans. And the same is true, the opposite, but less so, it's less pronounced. And the reason, if you put people in the magnet, is that the signal encoding for faces is much stronger in encoding faces that come from your own background, the faces they are used to seeing every day, rather than faces of other racial backgrounds that you're not familiar with. So the signal itself is different in the head. So it's not that people are biased because they're evil. People are biased because the signal is untrained for some faces. Okay. Now, there is an organization in the US called NIST, the National Institute of Science and Technology, that measures the bias, well, the accuracy and bias of face recognition systems. And I need to spend a moment explaining to you what these curves mean. And so you have two types of errors. The false reject rate, meaning you show up at the airport, you want to board your plane, and the machine says that you are not you. So the machine is making a mistake because it thinks that you are not the person you declare you are, versus the false accept rate, in which I show up and I say I'm Ricardo, and the machine lets me through. Okay? So depending on the application, the two errors may have different importance, and you want to minimize both, of course. And so these curves show you, for different settings of the machine in which you can trade off one error against the other by tuning a threshold, what is the trade-off for different ethnic backgrounds. And you see right away that there are big differences between people of different ethnic backgrounds. So I want you to hold this in mind for a second. Don't worry if you don't understand exactly what the plots mean. It's just important to remember that the curves are different for different ethnic backgrounds. And so you should assume, maybe, that the machine is biased and it's doing a better job for white and black people than for Asian and American Indians. Okay? So this is a problem, if it's true. And so I want to, in the next few slides, put a little bit of a doubt in your mind of whether these tests are to be interpreted in this way. Another example comes from a paper from MIT, which showed that algorithms for gender classification made more errors for black women. And so this was reported by the press as AI is biased against black women. And so for me, it was a big personal issue. And I'm working in a field that is biased against black women. It's not right. So what did this experiment look like? Well, what they did was collecting faces from the websites of parliaments in Africa to get black faces, and in Northern Europe to get pale faces. And in those parliaments, there were an equal number of men and women, and so they liked to collect, you see, the names of the countries. And they formed a data set with about 1,000 faces, and they measured the error rate in classifying gender for these 4 groups. And they found this, and the red and orange colors are the systems they tested, and then we reproduced their experiment, and we got the blue markers with our own implementation, which had less error, but still the effect was there.
Sorry. Okay, yeah, thank you. I was saying, considering all the level of biases that we know there are in AI as they are in the usual life, how did you select in your work the weight of each bias? Just to tell,
right.
Are you sure that you're not biased also in the choice of the biases to work on or to evaluate?
I see. Okay, so as an academic, I thought I would read the newspapers and I would see what people worry about, and I would try to dig deeper on those issues that were pointed out by the press. Now, there is always the worry that the press is not mirroring real concerns of real people, but they're just doing clickbait to tell you, oh, it's biased. But at the same time, it's the best I could do. And so that's how I decided to work on these questions. Now, I hope that by the end, we will see that what I talk about has fairly general applicability to any other question. So somehow you can see these as case studies, where we took a situation, we analyzed it, and hopefully people can replicate our methods to get to the bottom of whatever question they have. Is there a specific bias that you worry about?
Not specific one, but knowing the impact of the fact that we are anyway biased, even if we try to be unbiased.
Yes.
So there is not, it's not the gender one, there's not one specific, but really I'm curious because I like to read about biases also, but I'm not an academia person coming from academia, but I mean,
yes.
And so I was very curious to understand how instead you in some way try to limit it, because to exclude is difficult, I can agree, but to limit it, the intervention of the bias. Probably if having also, I don't know, I'm supposing having a group of work group with different genders, with different nationalities, this could also give or ethnics can give probably reduce the biases, for example, but I don't know if you consider something like this also.
Yeah. Okay, so what you're pointing out is very important. And so one thing I should emphasize is you see a lot of ethnicity questions in my talk, because in the US, ethnicity is a very important issue that people want to be careful about. Now, if I come to Italy, for example, it's rare that people worry about that, and it's more like men versus women. For example, I hear many women complain that men are treated in a better way in Italy, and of course, depending on our back life. And so, so my work is very US-centric in scope, but again, the methods should be general, and people should be able to use the methods for whatever. Yeah. Okay, so let's pick up again here. Okay, so went forward a bit. Okay, so so we're here. So the question is this a problem or not? And initially, you can think, yeah, there is clearly a problem. And then you think about it and you say, I don't think that this was done correctly for a very simple reason. So let's do the same reasoning on COVID mortality. And let's try to decide if the virus is biased against black people. Like, that's a reasonable thing to ask, right? And so you can look at mortality rates up to 2023 in 3 countries in Europe where there are mostly people with pale skin, and 3 countries in Africa where there are mostly people with dark skin, right? And so you look at the mortality rates, 300, it's very stable in Europe, and 10 or 11 in Africa. Okay, so you say, so the virus is biased against white people. And so you pause. I'm not convinced now, right? But this is exactly the same reasoning we did for the faces. Then we took a sample of black people, black women, and then we looked at the error rate of the algorithm. So this is called an observational study in medicine, and sometimes it's the best thing you can do. But we know that there are problems. What could the problem be? Well, for example, maybe the doctors in Sudan are better than the doctors in Italy, right? So who knows? Or maybe people in Sudan stay out in the outdoors and don't catch the virus, and in Italy they catch it. The explanation that convinced me most is looking at the demographic pyramid, where the median age in Italy is 50, and in Sudan is 18 or something like that. So this by itself could explain it, right? So we know that the virus is biased against all people. That we know. And so what happens then is that there are many things that correlate with a sample, with the skin color, the gender, and so on, and God knows which one of these is the cause. And really, when we ask questions about bias, we want to make a causal statement, like being a woman causes me to be discriminated against, and if I were a man, I wouldn't. So what can you do? And so here is just another silly example where somebody showed that how many Nobel Prizes a country wins per 10 million people is correlated with the chocolate consumption. And so you could say, well, so maybe if you eat more chocolate, it makes you smarter. Or maybe countries that win a Nobel Prize celebrate a lot and they drink champagne. But probably it's something different. I mean, there's a common cause. And higher wealth means higher education and also higher chocolate consumption and so on. Okay? So we need to resolve that, and we need to not stick just to observational studies where skin type and age may be correlated, and so we don't know if the high mortality rate is caused by the skin color or by age. And we need to be experimental, where we modify one variable at a time. But how could we possibly modify one variable at a time for COVID? I cannot take you and make you black, or make you old, or make you young. You are one person, I cannot change you. And so in medical studies, they try to balance groups. And so the question is, what about in AI? I cannot take my face, if I'm doing face recognition, and make myself black or a woman or whatever. How can we do it? So let me make this point clearly. If we look at this picture, what conclusion we draw about this man, and so we can say the man is probably sick. And I ask you, why is he sick? And you say, well, because he's in bed and because there are doctors. And so you say, well, so if the doctors and being in bed makes him sick, send the doctors away and tell him to get up, and then he will feel better, right? So we've made a prediction based on a correlation, and that's fine. But if we want to fix things and make him feel better, we need to know the cause. And so we need to know that the cause of the doctors being there is him being sick and not vice versa. So from observation, we can get correlation, we can get prediction, but only through an experiment where we change one variable at a time, we can get a causation, and then we can do intervention, which means changing the state of the world in a way that we want it to be. So how do we think about this case? And so somebody pointed out that there was one possible bug with the way this experiment went. And so here we go to a hypothesis of what could the cause be for the mistakes. And so the idea is that the hairstyle of parliamentarians is very conservative. So you don't get somebody looking like a Rastafarian or Jim Morrison in a Finnish parliament or in a Rwandan parliament. And the same for women in parliament, very few have a buzz cut. Apart from Rwanda, where a professional woman has short hair. That's a perfectly valid conservative hairstyle. So one hypothesis is, since the gender classification algorithms that were being tested are using the hairstyle as a proxy for gender, maybe they're being tested in a hard way only for black women, and they're not being tested in a hard way for the other cases where non-gender typical hairstyle are not represented. That's one hypothesis, right? So this could explain it. And so maybe it's the data set that is biased and not the algorithm. So how do we fix it? And so one idea is to do like in the medical profession. So you take me, I'm part of a data set, and now you're trying to find a match for me who is my same head shape and physiognomy and so on, but darker skin. And the best I could do was finding this guy, Bharat Hariharan, who was visiting the lab. I said, OK, he's the person who looks like me and has dark skin. Let's take a photograph. So you could do this and match subjects. The trouble is that it's very expensive, and you're never satisfied, and it's a problem. So the idea we followed was using synthetic faces. And so here AI comes to the rescue of AI. And here we used a mechanism called GAN, Generative Adversarial Networks, to generate synthetic faces. And now it has been supplanted in the last 2 years by diffusions. And some of you study diffusions, and so that would be an interesting idea to repurpose diffusions for this. But we use GANs. And so the question is, can we generate synthetic faces for carrying out experiments? And then maybe on synthetic faces, we can change one attribute at a time. And so that was some work I did with Guha Balakrishnan. And it is very simple. There is, in this generative method, there is a latent space which codes the appearance of a face as a point in a Euclidean space. And so you could think of a point associated to a woman, a point associated to a man, or to a face that looks like a woman, a face that looks like a man. And by the continuity theorem, so these maps are reasonably continuous, you can think that there must be at least one point which is neutral, where you transition from male to female. And so if you can find that point and you can estimate the direction of the normal vector to the tangent plane to that manifold, then you can probably walk from female to male, preserving all the attributes apart from the one you want to modify. So we started working on this, and as you can see, it was possible. You can change the apparent age, the beard, hair length, skin color. And for the people who like to think about geometry, there are interesting questions, because some of these attributes are correlated. And so if you look at the strip of faces at the top, and you start from the right, you have a face of a woman. And as you make the hair shorter, the physiognomy turns into the face of a man. So here you're modifying both. And so you've got to work in the geometry of a space and orthogonalize the dimensions. And then you obtain the strip that is framed, where if you move from right to left, it's still a woman, and just the hair gets shorter. Okay, so there are very interesting questions about the geometry of these high-dimensional spaces, and you've got to deal with them. And then, like in medicine, the idea is to have matched samples, where here we have 8 faces that have the same overall physiognomy, and you can travel from male to female, long and short hair, dark skin, and light skin. Okay, so the idea is that these faces preserve all the other attributes, like the geometry of the skull and anything else, the background, lighting, and so on. And the thing that changes is the thing you want to change. And so by comparing the performance of algorithms on these different faces, you can see if any one of these attributes is affecting the accuracy of the algorithm. And so since it's an experiment, you have a causal connection between the attribute and the face. And then how do we know that the algorithm is doing what you want? Like you could say, well, maybe the face you think is a woman looks like a man to humans, and so you should. And so you need to calibrate the whole thing with human annotators. And so the idea is that you've got to annotate an enormous number of synthetic faces, I think 500,000, for all of the attributes that they're interested in. And so it could be male, female, long beard, long hair, short hair, and so on. And then you can train a generator that will generate faces according to a recipe that you can decide on. And so this recipe could be change the hair length, or change the gender or sex. And then again, you send it to human annotators to verify that the algorithm, the generator, did what you wanted. And now you can compare the ratings of humans with the ratings of an algorithm and see if the ratings are in line. And then you can see if the gender classifier, which is a box in orange, is biased or not vis-a-vis some attribute. Okay? So it's a bit complicated, but once you think it through, it's not so bad. So the idea is that, and so we use two techniques, and again, I'm going to show them to you in a somewhat impressionistic way. In one case, we thought, okay, there's this big space of faces, and by fitting planes to it, we can estimate crudely what are the principal directions for gender, for skin color, and so on. And then we can orthogonalize them to obtain the results we want. There is another approach which is useful some other times, which is much subtler and estimates directly the manifold of constant physiognomy, and then allows you to move around attributes from that point on. And so this is, again, more subtle, but also quite effective, and you can use it too. And so here are examples where, just to demonstrate the idea, the seed faces are the left column, and the next three columns see you have a change in low spatial frequencies. And as you can see, the physiognomy changes, but the color and the lighting and so on remain the same. And the right columns, you change the low spatial frequency, and so all the color and light sources and so on change, and the physiognomy remains the same. This is just to demonstrate what you can do. And so now you have a bunch of faces, and how did we collect these human annotations? And again, we crowdsourced it. You cannot collect 500,000 annotations without the use of a giant crowd of tens of thousands of people. And so this is the user interface that these people see. And so at the top, you see the question, what is the skin color of the person? And they have a scale used by dermatologists on the left, and so they have to choose one of them, and then we take averages, and we get the ground truth. And so this would be an example. The strip shows you the transition from a female face who looked middle-aged to a younger male face, and the color of the skin changes, and you can see the ratings from the annotators as dots there, and you see that they change. And here is the change of gender. From the left, woman, right, a man again, and you see that the annotators change opinion about -2, and so on. And so here I'm showing you only one result, and we could verify that indeed what was biased in the original paper was the data set and not the algorithm. And so you see the original data at the top, PPB, and our synthetic transects, namely sections across these different dimensions, tell us a completely different story, namely the error rate is more or less constant across the different groups. Okay. So this is a case where it takes a lot of effort, as you can see, to convince yourself whether an algorithm is biased or not. And sometimes, since you have complete control, you can discover another bias. And so in this algorithm, it turns out that very young people get classified always as female. And so the bias really is, in quote, against young males. So that was the bias we found for the algorithm. So this is real bias in the algorithm, but not the original claim that it was black females that were getting misrecognized. You can do the same for face identification or recognition algorithms. So what we saw before was gender classification. and you can also do for face recognition. And so these are faces I took from the internet of actors who look like each other, but they're not the same person. And so so to me they look the same, but people who follow these actors are clearly saying that they're not the same person. And so again, you can construct faces where you can change the ethnicity. So each column is a different demographic group, and each row is a different physiognomy. And then you can modify different attributes like the pose, how are they oriented, to the left or the right. You can change lighting, you can change age, and all of this is done synthetically using GANs. And so you can just make it systematic and accumulate big numbers, the expression, smiling or not. And so here we saw that there is a subtle bias. It's not huge because you see it anyway, where recognition of black people for model 1 especially was not as good as the one for light-skinned people. And so that was something we could document, and we're quite convinced is true. So the last case study I want to show you has to do with CLIP. And so some of you know what CLIP is. It's a space where text and images are associated. And it's at the basis of a lot of mechanisms that you use nowadays, like generating an image using text. You get an image, and search of images using text. You search through a data set, and so on. And so it's important to know if CLIP is biased too. And so the idea we followed here was seeing what is the distance in a certain abstract space between an image and a sentence describing a socially relevant attribute. And so here the example you see is, well, for any one of these faces, which one responds more to the photo of a friendly person? Like, is there a bias whereby for CLIP, people of different sexes or national or ethnic origin might look more or less friendly? It's a reasonable question to ask. And social scientists have a whole taxonomy of attributes that have social relevance. And so this one has to do with, the friendly has to do with the characteristic of warmth, and then people are interested for competence, agency, belief, communion, and so on. And so I will not go into what these things mean, but you can intuit them. And so here are adjectives. And so I don't know if you can read, but on the left, trustworthy, friendly, honest, and so on have to do with warmth, and competence is competent, intelligent, skilled, efficient, and so on. And there are lots of different attributes that you can systematize and analyze. And so the idea is to generate a lot of sentences containing these attributes and compare these sentences with faces of different ethnicities and look at the variation also vis-a-vis, say, facial expression. And we get curves such as these ones. And so I'll go very quickly. So on the x-axis, you have different facial expressions, from frowning to smiling. And each one of these plots has to do with one of those socially relevant characteristics, like warmth, competence, conservative belief, etc. And what you see is that two things. One is that if you smile or not, it affects CLIP's judgment of you. And so if you smile, you will be judged as warmer personality, of course, right? And it has no effect on, say, conservative belief, okay? But also you see that different ethnicities and genders have different heights on the curves. And so something we saw is that indeed in this case, black females were being discriminated. And so those are the red curves with crosses. And you see that they are very different from the other groups. They're at one extremum. And so Asian men at one extremum, black women at the other extremum. So we could see that there is a bias in CLIP, and it's important to know it for people who have applications where this becomes relevant. Okay, so last thing I want to say is a message of hope and action for engineers. If people are biased, it's very difficult to unbias people. You can send them to courses and it doesn't work. You can talk to them. I don't know if it works. But as engineers, we can fix machines. As soon as we identify a problem and we know the cause of a problem, and so that's why causal analysis is important, we can do something about it. And what can you do? Well, typical thing you can do is collect more data of the kind in which the algorithm is not doing well. So this is a plot from one of my former students, Sarah Beatty, who is a professor at MIT, and she works on computational ecology, different story. But what you see is that for different animal species, the error rates are highly correlated with the number of training images. And we often, when you plot the error rate in log scale and the number of training examples in log scale, you see this beautiful straight line. And so we know that if we collect 10 to the 4th examples, we get about 1% error rates. But if you only have 100 examples, you get 10% error rates. So it's just a matter of money. Once you know that there's a problem, you collect more data. There are also other methods. I'm not going to cover them today. OK. So last slide. So I told you about responsible AI. What is it? I've told you about the question of bias and fairness and how to think about definitions and the fact that you need to agree in society on what goals you want to achieve. We've talked about the importance of being careful about correlation and causation. And only if you carry out experiments, you can figure out causation. And causation is what allows you to fix a problem. And then we talked about how to, in practice, how to measure bias in algorithms. Thank you.
Thank you so much. Are there any questions in the room? I see one hand here.
Hi. Thank you very much for your very interesting speech. I really, really appreciate your work, what you have been doing. I think that this kind of sanity check for AI methods are extremely important. I can agree with the colleague who said that there are a lot of different kind of biases, but for sure, the first thing that we need to know is that there are any bias in the model. It doesn't really matter for which, let's say, subgroup we are checking, but I definitely think that it's important to have a way to check it. And I was really interested by the last thing you said regarding the fact that if there are biases, we can try to fix them. And I was thinking if you had any idea on how to fix, if there is a way to fix a bias working within the model. So, for example, if you have an LLM, you have a VLM like Clip, if there is any way by checking the internal representation, moving in the internal representation along, for example, those linear...
Yeah, so, OK, thank you. That's a very good question. And I was, in the interest of time, I didn't go into that story. And so here is the issue. You can, for example, work on the loss function. And so here I'm using some technical terms that some people may not understand well. But the loss function is what makes the algorithm do what it does. So you could work on the loss function and put more weight on doing well in the categories where you're making more mistakes. And this will compromise performance in the categories that have less weight. Sometimes the compromise is tiny, and so you say, fantastic, let's do it. Sometimes there is a big problem. And so it would be like saying, suppose you have a treatment for cancer, and you realize that it works better for women than for men. And then you say, well, I don't like it. I prefer to make more women die so that we don't have a bias. Oh, that doesn't work so well, right? And so truly, you say, well, better fix the problem at the root and understand why it's not working well for men. And it takes more effort, of course, but it's the better choice. And so here, it's collect more data, annotate more data better, and so on. But sometimes you can do it without data. Yeah.
So it's 3 colleagues. So thanks as well. If possible, it would be amazing to get the slides because they're super, super good. My question is a bit more technical. In your causal analysis, one alternative would have been to train a sparse autoencoder and then label the latents so that you get what you call orthogonalization, so disentanglement for free. Then, of course, you need to label. So the idea is, of course, you get the latent for skin tone, you get the latent for gender, hair length, whatever, and then it possibly could be easier to manipulate, morph, warp these images into something else, and then submit them to the model for audit. I mean, have you went into that since it's the cool new tool in town?
No. So the answer is no, and that would be interesting.
Because
no.
we're working on that, so.
Okay. I'm happy to share our data, and so that would be very interesting to know if that's a better way to do it.
Lovely, thanks.
Yeah.
Hello. Yeah, thanks for the presentation. Very, very nice. So I wanted to discuss about the problem of measuring bias. So the topic of measuring biases. And of course, for measuring biases in models, you have to collect information about the data points, the protected variables of the data points, so you can check if you have these biases and also check for correlations and also causation. But there is a tension between having this information and also privacy. So you have to collect this data, and for example, if you get in France, you cannot collect information about specific types of protected variables like genetics, for example, is one thing, and other types of variables. So I wanted to discuss about this problem, and if you think that maybe generative models like you use it could be one solution for this type of problem.
Yeah, thank you. That's a fantastic question. So indeed, it's a feature of the method we use that we don't have to collect data from people. And just to illustrate the point that you're making even more clearly, people who work in this area face a double whammy. On the one side, you're not supposed to decide yourself what's the ethnicity or the gender of a person. You've got to ask them, right? And on the other hand, it's very intrusive to ask questions to people and ask them to declare themselves and then ask for permission and all of that. And the third one would be, okay, well, I build an algorithm that estimates what people will say, predict it, and the act of building an algorithm that decides if somebody is a man or a woman is, again, a very offensive act. It gets people really upset. Here, all the faces are synthetic, and so we can do whatever we want, in some sense, right? We can ask somebody, does this person look like a female or a male to you? So if you read the paper, we say that our measurements don't have to do with reality because they are about synthetic faces, and they're about opinions of people about synthetic faces. So what we measure really, it is how people's opinion about somebody's gender correlates or causes the algorithm to make a mistake. And so that's the... Thank you for your question, because it forced me to be very clear about what we're doing. Yeah.
Thank you so much. We are going to now move on to the round table. So I'm going to pass the microphone to Vittorio Di Tommaso, the moderator. Thank you.